So welcome to our meeting, a slightly exclusive gathering today, despite the publicity. And our traditional MC is not present, so I anticipated maybe that would be the case. So welcome. 2, any new people here? For this meeting, there's one new face there. If you could briefly introduce yourself, please. Gerard, and your interest is? Astronomy, yeah. Yep. And you're new to this? Yeah, and Peter is actually a long-standing member of the club in general, so his presence here actually validates the fact I've been trying to cross-promote this with one, on IAMA, which is our forum, our sort of internal online forum, and sort of try and get a little bit more mixing. Are you a new face here? Pardon? You're new here. Well, welcome to the SIG. Welcome to our special interest group called Microcontroller Interest Group. So we're going to do astronomy. It's cool. That's cool. Okay, anyone got any interesting news in the microcontroller or astronomy area? Now is about the time to speak up or forever hold thine peace. Or hold thine peace until after the coffee break. I don't really care. Hello, Brian. Who else have we got there? Joe. Who dat? Sorry, I can't. Are you a new face?
Yeah, I just signed up.
Okay. Well, welcome to the club. What's your name?
Byron.
Byron. What's your background, mate? Okay, right, well, there's something a little different again. And there's another face. Okay, our secretary's here, so you can validate his membership. You are still a member. No, you are. Oh, here's Byron. Oh, another one. Okay, the son of maybe a member. What's your name? Lyndon, tell us a little bit what you do. Sorry? Okay. Yeah, he's a very carey sort of a guy. Welcome to the land of lousy puns. Right, and okay, right. I should have bought a bottle of rum. Right, and son, what do you do? Okay, it's just interesting to know where people's interests lie and all that sort of stuff. And sorry, did I actually get you're into construction? Yeah, yeah. Okay, well, that's actually so. There's bigger mix of new faces than we've had before. So I think my marketing is working somehow or other. Isn't that cool? And a few people, regulars, who are missing. So that's the way it is. Good? Yeah, yeah. So I actually put this on the Bayside Community Hub on Facebook, which has got 20,000 members. So there's huge coverage, but it's mainly young mums who've lost their puppies and that sort of thing, and an occasional child. Yeah. G'day, Max. You're not new, but I can't say you're old either. That won't be very nice at all, would it? Okay. So now I'm going to do a little promo for what's happening on Sunday. The new-ish Science Technology Group, which is something that's been formed also as a result of marketing efforts. Sorry, I'm not meant here to plug my marketing efforts, but that's the way it's working out. Are doing an experiment with gel electrophoresis. So it's the Science and Technology Projects Group, and basically what electrophoresis is, or gel electrophoresis, is you get yourself this piece of gel. It's an agar gel, cast in a shape something like this. It has electrodes at either end in there, and in there in the fat bits. It has some little wells here that you put your samples into, which might be a DNA sample. And you apply an electric current across there, or a voltage. We've got a 48-volt power supply outside that we're going to use on Sunday. And the molecules will start on, it's filled up with an electrolyte, which is just, what are we using? Bicarb of soda. Just a weak bicarb of soda, which is also in the gel. And when you put the voltage on, the molecules start to migrate down there, but at different speeds according to the molecular weight. So it actually separates the molecules into different molecular weights, and then you can get an idea of what the composition is of your sample. A very, very good question, Joe. And the answer to that is, look, this is not my expertise, but you can buy something called a DNA ladder, which is a sample that contains a mixture of known, they call it base pair lengths or something or other like that. Or, yeah, the molecules in the DNA sample have different numbers of base pairs in them. And this ladder has a known mixture of them. So when you do that in a cell here, it stretches out and it becomes a ruler. Yeah, referencing, exactly that. And it took me a while when I first saw that. I wasn't taking that much interest because upwards of $50 or $60 per pop for these things. So it's not something we're going to be using here on Sunday. We're actually probably going to be using food dye. You take green food dye and you put it through there and you get a blue band and you get a yellow band. And I think that'll be really cool. So if that sort of sounds interesting, come on, have a play. Okay, now, anyone got any show and tell? Anything you've made? Want to tell us about? Any problems you've had? Not with your wife, but technical problems? No? All quiet? Oh, good. That's a good one for John. Okay, we won't go any further on that one. Thank you very much. Yeah. Taking that a little seriously, makerspace, yes, but the thing it's called Science and Technology Group. And one of the really, really exciting things for me personally is that there is now talk within that group of doing a hydroponic setup. And the hydroponic setup is not so much to grow something or other, as to be able to, for me at least, I'm attracted to the idea of being able to do comparative experiments, maybe split it into an A and B side, and see whether something or other grows best with ultraviolet light or with red light or mixed daylight or what have you. Just kind of cool experimentation. So I'm really looking forward to that. And it's a project that will allow a number of people with a number of different skills to contribute. Yeah, it's an official SIG. Yeah. It started because, Claudio has actually been to one or two meetings, and we'd love to see you again, maybe on Sunday, and come and play with this. Pardon?
The next one sounds really interesting.
Yeah.
I've been looking into doing some business in that direction.
Yeah, okay. Right, well, there you go. The hydroponics thing, it's a multi-skill project that we can have people within the groups collaborating on, and that's what I find attractive. I mean, personally, I can sort of bring electronic controls to the table. We've got a couple of guys who are really into plants. We've got people who are into construction, to physically construct the framework and all that sort of stuff. So all we need is a plumber, probably, to get the plumbing right. So, construction, there you go. Okay, so without further ado, I'm going to hand over to Claudio. Claudio, without any notes at all, is a mathematical astronomer.
Mathematical physics.
Mathematical physicist, okay, which is different to a physical mathematician. And he's going to talk about... Over to you.
So I will be talking tonight about a bump, a wiggle, and a blob. So the idea to this talk basically came about, so in somewhere beginning of the year, David asked me whether I'd give a talk, and I was like, yeah, sure. And I had no idea really what I would want to talk about. But then on April 10th, the last of this triplet with this beautiful blob here was published, and I actually put this up on Facebook with exactly that tagline. And the point is, why I put this up is essentially these three things that amount to a bump, a wiggle, and a blob are the summary, the entirety that is the amazing progress of fundamental physics in the last 10 years. And these three things, these were huge experiments, which I will talk about shortly. And all it boils down to on the data level eventually is you get to see a bump here, you get to see a wiggle there, and you have some blob. Now, let me get into the... So, let me get an overview and why I consider these... why it's so special that's essentially a bump, a wiggle, and a blob. Because when you look at what's behind those three fairly simple images, it's a gigantic scientific effort. So the first one to start off is the bump. That comes from CERN in Switzerland, and it's Large Hadron Collider. So the CERN was founded in 1954 and was first built for the Large Electron Positron Collider that was used from 89 to 2000, and then afterwards the LHC, so the Large Hadron Collider that is today in use, was built in the pre-existing tunnel. So the Large Hadron Collider was first turned on in 2009, and it is still operational today, so it's still generating data and hopefully some additional insights, and additional upgrades will allow it to run approximately till 2035. Now, the most important point that I can't stress enough is this simple picture that is so important for our understanding of the physical world is a huge team play. So on the first Higgs paper, there were a total of 2,932 authors. So these are all the people that in some form contributed to that result that gives us this understanding into the physical world. A follow-up paper even beat that, and I think it's the current world record with 5,154 authors. And the CERN, or the LHC, is with a budget of about 7.5 billion euros, the single most expensive research infrastructure in the world. This is just one picture that I found of people. It's just, I can't emphasize it enough how many people and how many brilliant minds were involved in these results. On the second, the wiggle is a result of the LIGO-Virgo collaborations. And the original proposal, the prototypes, go back to the 1960s. The first stage of LIGO was built 1994 to 2002, the first observational run from 2002 to 10 yielded no results. It was then upgraded and ready by 2015, and it's in operation since then. The total construction cost for the LIGO, just for LIGO, the 2 observations in the US, comes down to about 620 million. That's about 1 order of magnitude less than the LHC, but still a huge amount of money. The additional de Burgo Observatory was founded in '93 and operational by 2003, and it was upgraded then until 2016. And the 2 projects basically joined forces in 2007, and hence it is always joint collaboration between them. Now here we have again the detection paper. So the first gravitational wave result featured a grand total of 1,011 authors. So here again, it's an effort that spans several decades. So if we exclude the preliminary dates, it's still more than 20 years to get the first actual observation going, and it involved a grand total in the end on the paper of more than 1,000 authors. Now, the last one, this is a little smaller. The collaboration was launched in 2009, but here it goes to say that it built on a lot of pre-existing telescope infrastructure. And therefore also it was hard to really come by an actual number for the project costs, because there's a lot that went into the Event Horizon telescope that's hidden in essentially construction costs of different telescopes that have broader applications. My rough guesstimate, and this is absolutely non-reliable, is probably somewhere 120, 150 million. The number that I know is that one part of the project, the Black Hole Cam, that's funded by the European Research Council, was 19 million just the project. On top of that, the ERC founded 3 full research groups, I think for about 10 years, that were working on that. So I think the guess is probably not too bad. I would expect it rather on the lower end. And again here also, the black hole paper eventually had 349 authors on it. So this is something that I really can't stress enough. Modern research in foundations of physics is to a large extent teamwork, and we're talking on teamwork on a massive scale. So in the following now, I will go a little bit into the background of the different experiments and explain them as far as I can. I have to admit the order of discoveries are also in order of my expertise. So the first one I'm vaguely familiar, and then it gets better. So this is just a little warning in the beginning. So CERN is essentially a 27-kilometer tunnel at the border between France and Switzerland. So you see the border is running somewhere here, and the tunnel circulates through it. So when the protons circle in this accelerator, they pass the border quite many times. Now, the task of CERN, or what CERN is concerned with, is particle physics. So this is our collection. This is the standard model of particle physics. It's made up of the fermions here that come in 3 generations. So we have the leptons, so the electron, the muon, and tau. We have the neutrinos, which come in the corresponding flavors. And then we have the quarks, which are the up and down quark, charm and strange, top and bottom. We then have here essentially the gauge bosons, which is the gluon, the photon, which is probably the best known, the Z boson, and the W boson. And this is what we knew we had before the LHC went into operation. Now, there is a mathematical framework to order all these particles in a consistent manner, but for this to work, one needs one additional particle, namely the Higgs. So, without the Higgs, the standard model of particle physics is mathematically inconsistent. And that's why people were looking for it. Now, the way this is done is with huge accelerators. So here just some pictures to give you a rough idea. So you have, these are the tubes that are in the tunnel where essentially the protons circle around. And then you have the collider infrastructure. This one is the Atlas detector, if I'm correct, where the protons are then smashed into each other. So for the CERN, this is essentially, you have one accelerator, but they built 4 different experiments. So there are 4 different colliding points where the beams are focused. This is the Atlas detector, which main purpose was to search for the Higgs and for new physics. The CMS detector, which was also for the Higgs and new physics. ALICE, which is to study the quark-gluon plasma. And the LHCb, which is for matter-antimatter things. Now, you might ask, okay, we have Atlas and CMS, we have 2 experiments which have the exact same task. And you might ask, why do we have that? And it's pretty simple. You need, if you want to have reliable information, you need to have a result confirmed by multiple sources. Now, the point is we only have one huge proton, lepton as a Large Hadron Collider, right? So, to get reliable results, you essentially need to have 2 independent measurements of the same thing. So that's why basically they had to devise 2 different detectors to observe the same thing. So this is not a double thing, but that's actually a necessity. Now, some of the technical details here. In the LHC, you have 2 proton beams that orbit that counter orbit around this 27-kilometer tunnel, and the maximum energy at the moment is about 6.5 tera-electron volt per proton. Now, the proton has a rest mass of about 1 giga-electron volt, so the kinetic energy is about a factor 6,500 of its rest mass. This basically means that the proton is going pretty much almost the speed of light. So it's like 0.9999999 times the speed of light. So this is, so they are going around the circle extremely fast, and when they collide, of course, you get the kinetic energy of 2 of them. So one collision that then gives like a trace pattern amounts to roughly 13 tera-electron volt of energy that is released on the collision point. The infrastructure, the tricky thing of the whole experiment or the precondition is essentially that you can have the protons at this energy go in a circle. And for that they needed 10,000 superconducting magnets, and they have field strength of up to 7.7 Tesla at the moment. And this is, as a comparison, your typical magnetic resonance imaging device operates about like 1.5 Tesla. So these are pretty impressive field strengths that are used to keep those protons on track. The superconducting part basically makes the requirement that the whole system, the entire 27-kilometer tunnel, is operated at 1.9 Kelvin. this is cooled with liquid helium, and I think CERN has something like a quarter or so of the world usage of helium goes into CERN. This number is rough, but it's gigantic numbers when you look into it. The energy consumption of it, so the energy consumption is actually so high that the operating time is usually put into summer when electric power is cheaper. So operation in winter is very exceptional because power is more expensive. So these are extreme energies that they use, and also extreme data that they produce. So this is about, now in operation, CERN produces about 25 petabyte of data per year. And this, of course, all has to be processed, and actually getting it away from the detectors, I think, is one of the biggest challenges. And here, just to mention a couple of the obstacles to go to higher energies, these are mainly two. So one is the magnetic field strength, so you need to be able to contain those protons on a circle. And the second problem is actually the energy loss. So most of you probably know, if you have a charge and you accelerate it, it gives off radiation. And essentially, when you spin around protons in a big circle, there is a massive acceleration there if it's going almost the speed of light. So there is a huge loss of energy due to synchrotron radiation from that spinning around. And so those are basically the main obstacles. So both, to some extent, relate to the circumference of the of the collider, which I will mention something on later. So, yes, yeah. So actually, to have these 6.5 tera electron volts, yeah. I think it's actually not an awful lot, because you have to keep in mind how much the how small really protons actually are. So you have in 1 mole of atoms, you have, what was it, 6 times 10 to the 23, I think? 23. So this converts atomic units into grams, right? And so basically a proton has one atomic unit. So you need 6 to the 23 protons, and this is roughly the energy of 10 to the 3 protons. So of course it is the entire mass energy of it, so it's still a lot, but we're still talking something, the mass energy of a lot less, of like something like 10 to the minus 19 grams. So I'm not quite sure. I can't make the immediate conversion into everyday things, but these 13 tera electron volts probably don't boil down to all too much actually when you compare it to everyday energies. Yes. That sounds, I mean, it always, so I mean the beam comes in at a very so the beam is very focused, right? So if they hit it at the concrete, it's probably going to be in a very narrow region. So all these questions come down to energy densities, right? If you focus it on the beam on a very small area, then it is quite plausible, because there is something, I think, like in every bunch there's a couple 10 to the something, 10 to a couple orders of magnitude protons are actually in each bundle. So this is then, of course, the energy of the actual beam is much higher. Is number of protons times this 10 to the 13 tera electron volt. And there are and the thing actually is not, it's not one package that goes around, but it's a whole bunch of packages that go around that come in spacings. I don't remember what exactly was it. I had a look over the numbers. But so yeah, I can imagine very well that the total kinetic energy that's in all protons that go around is fairly big. And then of course, to get a temperature is just basically energy density. If you get locally, if you all stop them within a very small region, then you get very hot. I mean, that's basically the point here, right? This energy on collision is basically on the space of two protons. So the temperature that you reach there is extremely high if you calculate in temperature, which is of course very hard to do, because temperature is essentially an averaging energy average, but still you can roughly assign that. So this all boils down essentially to energy densities, if I may leave it at that. So here the result. The CERN in 2012, they announced that they found a new particle at roughly 127 giga-electron volts with the correct properties for the thought for Higgs boson. So of course there were all the other collisions that didn't necessarily produce the Higgs, but that still produced a lot of additional data on the existing standard model, and it essentially confirmed the standard model to an ever higher degrees, and especially the matter-antimatter asymmetry, for example, is further constrained, and so on and so forth. And the most important aspect here, to some extent, is actually that besides the Higgs, there was not really anything new there. There was really quickly this short flare that you probably heard of the superluminal neutrinos. This turned out fairly quickly to be just a measurement error. But so the most important aspect, essentially, besides the fact that they found the Higgs, which is amazing, is also that they didn't find anything else. And I will get into the relevance of that finding more towards the end. Now, in 2013, this then famously led to the Nobel Prize for Higgs entanglement. On to the next one of our three pictures, the LIGO-Virgo collaboration. So these here are the two LIGO facilities in the US. This is the one in Livingston, and here in God. Now I actually I have it on Hanford. Yeah, Livingston, Hanford. God. Okay. And essentially what this is, it boils down technically to two giant interferometers. So there are two laser beams that run down these arms, and then essentially you measure the change of length in these arms, but more on that further down. So these are the facilities, and here we have what is actually trying the physical origin of what it's trying to observe, namely gravitational waves. So what you see here is a rough, is a simulation, numerical simulation of the in-spiral of two black holes. And you see here at the bottom how the shape of the gravitational wave that goes out and running out. So you see here outside in the blue and purple, you see actually the wave fronts that go away from the collision. And so you see how the frequency and the amplitude builds up until very much at the collision, and then you have a short ring down, and then it settles into a new individual black hole. So that is basically what the theory tells us. If we take Einstein's general relativity, put in two black holes, put it on a computer, see what comes out, tells us, looks like that. So if Einstein is right, we should be able to observe it. Now, to mention, these are right here at the event. These are gigantic energies that are set free. However, they travel through space and disperse. And the eventual effect is extremely tiny. I will go more into details here at the end. So what we have here, how the thing works, what you saw before, these two arms, these are essentially just giant cavities. So you have an initial laser here. So this is an interferometer. So you have an initial laser here, and then it has only basically about 20 watts of power that is generated, that it inputs through a first mirror, and then onto a beam splitter. Now from the beam splitter you have one half of the beam goes down this arm, the other half goes up that, and when it comes back, then if it's on phase, this part here actually cancels out. So if nothing happens and the phases are aligned, the detector down here will not see anything. So this is if it's just sitting there and nothing happens. Now, if a gravitational wave passes through, what happens is that actually the length of the arms are affected differently. So when one gets stretched, the other one gets actually squeezed. And so what happens is that the photons that travel here have acquire a different phase along their path than the ones that are in the other arm. And therefore, when the gravitation wave passes through, you get a different phase shift here, and actually now suddenly, instead of having 0 photons go down here, you have some coming through. So the amount of photons that arrive here basically relates directly to the differential stretching and squeezing of the two arms. So the arm length here is basically 4,000 meters, so it's like 4 kilometers arm length. And the additional cavity is to enhance the effect. So the change of length per arm due to gravitational waves is 1/10,000th the diameter of a proton. This is incredible. It's like you really have to think. If you look in, I can just recommend to look into the technical detail, the technical length they had to go to build an instrument that was this sensitive. So among others, these actual additional mirrors here serve the purpose that a single photon doesn't just transverse this arm once, but transverses it many, many times, and therefore building up, so enhancing the effect. Yes?
How do you manage to cut out the natural things that come as, heat and cooling and
I will get to this discussion very soon.
Thank you.
And so what it's operated at is about, the wavelength is 1,000 and rough something nanometers, and so these 20 watts are in here in the cavity. You actually have in the end 100 kilowatt of beam cycling through. Now, exactly for that purpose, and the next slide to come, the two facilities are separated geographically. This has another aspect which I will mention later, but one of the core aspects to it is that the environmental noise here and here is substantially different. So this is it's again the same thing. You need to have two experiments to have a confirmation. So building one of these by itself would not have been sufficient for a first detector, because it could always be something weird. But if you have a consistent wave result here and here, then you can be sufficiently certain that you actually observed something. Now, the main point to what you come to, with this sensitivity, all the engineering boils down to is noise, 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 noise. So so you have different. So here, essentially, you see what the different noise sources are, right? So you have basically the radiation pressure. So you have 100 kilowatt of beam in this cavity. Now, that basically means every time a photon hits the mirror, it transfers some momentum onto the mirror. This by itself is a substantial source of noise. This is the radiation pressure. Then you have the shot noise that I'm not entirely sure what it is. Then you have seismic noise. This is basically telling...
Shot noise is because it's located in Texas.
Only one of them. and then you have basically here, okay, you have the thermal noise of the mirror suspensions. I will show you how the mirrors are suspended afterwards. And then you have the thermal thing of the mirror. I think, so here you actually see the noise budget of the different detectors. So the red and the green are the two LIGO detectors, the blue and the turquoise are essentially the two Virgo detectors. And I think it is this peak here actually that somebody told me, I'm not 100% sure, but so the geometry of the mirrors is designed in a way that thermal noise accumulates in one particular frequency, and so you can get rid of it. So you collect all the noise instead of getting... So this is essentially the length they went to essentially get rid of noise or collect the noise in single frequencies is amazing. This is the crazy thing. So here you see how the mirrors are suspended. So first you have, this is just an additional rest mass, which is suspended on steel wires, and then from this mass you have two silica threads that go down to the actual mirror, and both of these mirrors have 40 kilograms of weight, and this is this double suspension. And I heard once, I'm not quite sure, but these silica fibers are extremely thin. So this is the setup of the mirrors that are used actually in the detectors. Now, an additional problem that we have here is the whole data analysis, because when you have a gravitational wave event, this is a very short occurrence in time. So this is a single occurrence. Every observation, every collision is a single occurrence. You can't reproduce it. So you need to have a pipeline that is safe to false interpretations. And so among other things, what they actually did in the first run, they have a mechanical mechanism that they can feed a mechanical simulated gravitational wave signal into the mirrors, so they can basically fake a signal on command, to test the team. So one of the board members can just go up one day, press the button, shoot a signal in, and then the whole collaboration works it up as if it's an actual occurrence. And at the very last step, before they're about to submit, the person who actually put in the signal comes up and is like, sorry guys, it was just a test. And that's what they actually did. And this is very crucial to test against bias, because you want to find something. So you have to vet your pipeline to make sure that you don't detect something just because you want to. And then, as a result, we got this beauty here. This is the first one. These are the two. And I'm going to be shut up. So you hear the characteristic chirp that you get from the gravitational wave signal. So you see here the waveform that they got out. It looks roughly like the theoretical waveform that I showed you in the beginning. So you have an increase in frequency, and this gives this characteristic chirp noise that you heard now. Of course, the noise was actually scaled a little bit, so in the original frequency it wouldn't really be audible. So, but if you scale it a little bit, you get a chirp that you can actually hear, and this is pretty cool. So this was the first observation in 2015, was announced in January 16. And so the result is the first observation of gravitational waves. This is, of course, the most outstanding result. By now we have dozens of black-hole mergers, and what's the second important thing here, it is actually testing the existence of black holes, right? Because the waveform you get out is very crucially depending on what kind of objects collide in the universe. So this result and the exact shape of the signal tell us more than just that we have gravitational waves, but also that black holes are out there and that they are colliding. And they are colliding exactly in the way that our theory tells us that we should expect them to collide. Now in 2017, I think, another extremely important event was the first neutron star merger, and with it comes the advent of multi-messenger astronomy. What we had up to the day, or up to 2015, astronomy basically relied on the electromagnetic wave spectrum. So you had different frequencies, you could look at the sky, but essentially all we could have was light of different frequencies. There were already some neutrino experiments that give now also additional information. But now with the gravitational waves, we have actually a completely different tool to probe the universe. And this neutron star collision was the first time that this multi-messenger astronomy really came to weigh in. So they saw the signal, they alerted all the telescopes around the world, and all of them peered up into the sky. I think if you take all the papers that were published on this together, it was something like 40,000 authors, because every telescope that observed the event produced their own paper on it. And every telescope on its own is a collaboration of the size that we talked about. So the number of people involved in these results is far greater. And actually what this showed us was that indeed neutron star mergers can provide us the heavy elements in the universe. Because so you can do the budget. You start off with a universe that has just protons and neutrons. The Big Bang or inflation essentially gives you some hydrogen, gives you the hydrogen and some helium, and some lithium, and then the stars burn things and produce up to iron. Supernova can get up a couple higher, really. But then your production rate is not high enough, so the supernova don't really provide sufficient high mass, so heavy elements. And they could show here basically that the neutron star mergers, then, since with all the neutrons that are getting blasted out, can in fact produce the heavy elements, and sufficient abundance, I think, but that will be up to future observations, because so far that's just a one-off event. Now this is more an outlook, actually. As the events pile up, this will substantially improve our understanding of the universe. And again here also, so far no new physics. I will give a slight discussion. There's some ideas how you might be able to detect new physics in here. And of course the other result here is the Nobel Prize 2017 for Barry Barish, Kip Thorne, and Ryan Weiss. The third founder of the LIGO collaboration actually died before the Nobel Prize, and that's why Barish, who was the operating since, I think he was the leader of the LIGO collaboration since 94 or something, was the third one besides the founders, the founding members, that got the Nobel Prize. Now, to the last of the three, this one is the Event Horizon Telescope. And this is a network of 6 telescopes that's spread out across the globe. So you have one at the South Pole, then you have Atacama, then you have Mexico, the US, and again the US on Hawaii, and one here on Tenerife, I think. And the important thing is these telescopes, so you have radio telescopes in all these places, and what they do is they're connected together. So with a very long baseline interferometry, you can basically couple the observations from these together, and it more or less acts as if it were one giant telescope the size of the planet. And now, what is the goal of the Event Horizon Telescope? Well, so as I said, we know black holes exist, and in particular we have we have at the center of our galaxy, we have Sagittarius A star. So we have this object here which emits almost no radiation, but when you trace stars around it, you see they go in extremely narrow orbits. So you can more or less calculate the amount of mass that has to be in there, and it's a couple million solar masses or more. And so the best explanation we have is, okay, there's most likely a supermassive black hole in there. And that's Sagittarius A star. And the second black hole that is within reach of the resolution, theoretically, that's Messier 87 star, so M87 referred to usually. Now, what are we trying to see? So, you know, the basic understanding of black holes that you get repeated and everybody tells you is right, is nothing gets out of a black hole. So, what do you hope to see about it? Now, here I drew a little sketch. So, suppose that's me, and I'm sitting somewhere close to a black hole, and I have a laser. Now, I can direct this laser. Basically, I can choose between different directions. So I have a sphere of different directions I can point. And I can ask questions, where does my laser end up? Now, obviously, if I point it at the black hole, it goes in. If I point it away, it goes out. And somewhere in between, there is a boundary. So we have some directions that end up in the black hole, and some directions that go out to infinity. So now what we want to do, obviously, we can't shoot the laser and see where it ends up, because we're in the universe. But we can turn around this picture, and we can look at background light from star or gas or anything that's out there. And now basically what this tells us is that any background light that reaches us cannot come from these directions where the black hole is at. So no matter how much light we put around it, there will be a dark spot on our sky when we have a black hole in our neighborhood. And this is essentially what the black hole telescope tries to observe. And here, the technical details, as I said, it's a very long baseline interferometry. They operate between 230 and 450 gigahertz. And yeah, so as already mentioned, it's effectively a telescope the size of the Earth. This gives them an optical resolution of about 25 microarc seconds. And the example that is usually used that I just adopted is that 25 microarc seconds, that means when you look from here to the moon, you put an apple up there, you can see it. So you can resolve an apple on the moon. That is the resolution that they need to produce this picture. Now again here, so what you see in this picture is you have the radio signal, and you have atomic clocks, because you don't only need to register the frequency, but also the phase of the incoming light at every telescope for the interferometry to work, so that you can correlate the signal at different times, at the same time at different places. You need all this information, which boils down to a shit ton of data. And this is actually one of my favorite facts about it. The amount of data is so big here that for the telescope at the South Pole, the quickest way to get the data, so they have to observe in April, because that's when this side of the planet is directed towards these black holes. And that's when winter starts at the South Pole. And the fastest way to get the data from the South Pole is to sit around 6 months, wait until it gets summer down here, fly in, pick up the hard drives, and fly out. This is literally the fastest way of data transfer. Yes?
I would just like to commend those guys on not signing up for the NBN.
And then, of course, this resulted in this famous picture of the M87. That's now our first picture of a black hole. So from now on, when somebody asks you, what does a black hole look like? This. And what you have here is, so what you see is a black hole. So the important thing is, I said you need background light. So this is not 100% correct what actually happens, because when you have a black hole, you have hot gas. You have gas that's infalling, that's spiraling around the black hole. And that is what emits the light that we observe. So this is essentially a hot disk of gas around the black hole that's circling around it. And that emits the light that we then observe. So we're not quite having the background light, but the light is somewhere in between us and the black hole. So there is a little, so it's not quite an absolute dark shadow, but it's pretty close on. And the important thing is, what you see, the asymmetry, is actually highly relevant, because that gives us the information that, so the gas roughly on this side moves away from us, and from here it comes towards us. So it gets Doppler shifted, and you get a higher intensity in the direction of motion. So this roughly tells us some information about the spin of the black hole and its disk. Now, here again, no surprise. Sagittarius A star, so our very own supermassive black hole, they couldn't resolve. I didn't dive into what the issues were exactly, but I think it's too variable. So this M87 is much bigger, but further away. So they have about the same size, the same effective size on the screen. But the fact that it's much bigger has the advantage that it's a lot less variable, because even if the gas is extremely fast, to go around once will take a pretty long time. So the constellation is fairly consistent even over the observation periods, while our own one is, well, I think it's one of the smaller supermassive black holes. Actually, take this with a grain of salt, but having a smaller black hole basically means the length scales are smaller, so if the gas is hot and moving fast, you have a lot more variability. While if the black hole itself has something like 1 light year in diameter, the gas can move basically as fast as it wants. If you observe it for a couple of days, nothing really changes that much on these scales. Now, one thing that is still open, this is potentially we will be able to determine the spin of the black hole. So far, we have no black hole where we can do this very well. So, now to the last bit, and now what? So, I emphasized on all these bits, we have no new physics. So, this is kind of, physics is in a sense cursed by its success, because we have two theories that are extraordinarily accurate, and that now in this past decade have been confirmed and completed, and to a very high degree. However, on the fundamental mathematical level and philosophical level, they are incompatible. And with these experiments that we now had, none of them gave us any evidence where to look for a new theory, so where to go ahead. Because essentially all of them, they confirm what their particular model predicted, but not much new. So there's no defect that gives us any sort of hint. When you look at the advent of particle physics, it was to a large extent, and quantum mechanics, it was very much a step race between observation and experiment. So it was basically the theoreticians came up, or the experiments had a couple new particles, asked the theory guys, please explain. Theory went, okay, we can explain it, but it would need 3 more particles. Then the experimenters went back, oh, we found 7 more. And this stepladder essentially, and this essentially inspired each other and led to a very rapid development. But now, essentially, on the theory level, so the standard model was completed from the theory side basically 40 years ago. General relativity is more than 100 years old. And since, on the theoretical level, I would claim we have made very little progress to actually unify the two. There's no newer theory, basically, on the fundamental level that has any clear predictions that we could be hunting for. And, well, so it's not quite true. We have, of course, very few hints, namely from cosmological observations. And that includes matter-antimatter asymmetry. Why are we here? So when we smash particles together and here on Earth and we produce particles and antiparticles, they come in a perfect symmetry. So far there's little violation of that. This begs the question, well, why do we actually exist? If you look in the universe, we have matter, but very little antimatter. So something must have happened at some point. The second thing, of course, is the postulate, the hypothesis of dark matter that is supported basically by observation of the cosmic microwave background and by the rotation curves of galaxies. Dark energy, similar thing, different observations of the expansion rate of the universe. And then, of course, related are issues all around Big Bang and inflation, which basically feed into all of these issues. So, in particular, the fact that at the LHC we have not discovered any new physics, this poses a problem to several attempts to unify physics, namely everything that's basically reliant on supersymmetry, in particular string theory. Because those theories say that there is a whole slew of additional particles, and so far they just haven't shown up. So this is pretty bad news for those. Even though people working on these, they will claim, yeah, they're just at higher energies. So we just have to build stronger colliders, which is what I'll be talking about. And so my take-home message on the current situation really is that without good guidance from experiment, we should really pursue a very open-minded approach to theory, to model development. So take every idea into consideration and actually take a step back, look again at the foundational problems, the foundational conceptual problems that make the two theories incompatible. And the open-mindedness especially goes that there should not be any such thing as an only game in town as long as we lack hard evidence for one particular model. So now kind of like what is the outlook on observations? The gravitational wave track is certainly the most promising for future observations. This is the LISA mission, not quite yet mission I think, but the proposal. It puts the laser interferometer in space. Now instead of 4 kilometers arm length, you get a couple million kilometers arm length. And so it would be, the 3 satellites would be located around one of the Lagrange points. So it would be trailing behind Earth as we go around. And this is one of the stable points in the configuration, but that's a different story. And what this gives, this is something I forgot to mention actually. The second reason why you want to have 2, or actually why you want to have 3 interferometers, is that you need them to triangulate your source. So every interferometer can basically remove 1 degree of freedom of the direction. So once you have 3 observatories, you can actually triangulate the source in the sky. So the first signal, they could only tell you from which strip in the sky it could come from, because that was the only what they could constrain. And the way this is resolved with LISA is essentially it will catch the signals way longer. So the current detectors, they observe the last couple milliseconds, nanoseconds of the in-spiral. LISA will be able to observe gravitational wave sources for years, and therefore the triangulation here happens basically that it observes the same source while it goes around the solar system and changes its own orientation, and therefore by figuring out one source here, here, and here, you get the triangulation and you can identify the sources for different black hole signals. One issue that they will have here is actually an abundance of signals. So now you will have multiple sources at the same time that are within the visibility range of the interferometer, and that gives you an overabundance of signals essentially. Now here, for that mission, this is the noise. Again, the most important thing is noise, 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 noise. So before shooting up a couple $1 billion into space, they launched the Pathfinder mission. And what you see here, this was the noise, the Pathfinder mission requirement. That was like, okay, if we manage to get that, future development will be able to get us down to LISA requirements. Now, the blue and the black is the actual noise spectrum they recorded. So the Pathfinder mission essentially already satisfies the LISA requirements with respect to noise. So this, as a result, plus together, of course, with the actual observation of the gravitational waves, put LISA as a selected L3 mission in 2017. So now the mission design can be completed and it will be proposed for adoption, and we can expect LISA to fly in roughly 2034. So this is obviously usually plus or minus 5 years or something. And yeah, the big advantage will be higher sensibility. And for the Event Horizon Telescope, there is one Sagittarius A stars outstanding, and there are proposals, I heard, to build a space-based, very long baseline interferometry. Obviously, it has already, the Event Horizon Telescope has the diameter of the planet. There's literally nowhere you can go with size except to space. I can't comment on that feasibility. Then, as I mentioned with respect to the collider, the main issue to go to higher energies is circumference. So there are proposals and there is lobbying to build a new circular collider either in Switzerland, and I think there's also some proposals going around for China. That should then be roughly 100 kilometers round long, and they'd hope to get up to 100 tera electron volt collision energy, so roughly 2 orders of magnitude higher than we have now. On the technical side, the development would need about double the magnets, double the magnetic field strength. And the price tag is, with roughly 20 billion, pretty high. And so one of the central questions, and this one I'm actually skeptical whether it's worth it. I'm all for investment in fundamental research, but with the current state of theoretical predictions, investing 20 billion in a happy-go-lucky project and just in the explorative sense, I think it would be more efficient to go for other fundamental projects. Namely, there are quite a lot of other experiments, also very interesting ones, that go on in fundamental physics. There are all the dark matter searches so far. Most of them have returned 0 results. There's one notorious signal from the Dama Libera experiment in Italy that claims a result, but nobody can confirm it, which they try to replicate. I think actually one down here in Australia to eliminate seasonal effects on the northern hemisphere. Then there are all the neutrino experiments. Neutrino experiments are notoriously difficult because neutrinos don't like to interact. So these are very tricky experiments. Then there are a couple very cool approaches to do tabletop quantum gravity experiments. Essentially, the idea is you have 2 pendula that only interact gravitationally. And now the point is, if you manage to cool them down sufficiently that their position becomes governed by quantum mechanics, and you excite one of them, now if there is an interaction, then you should expect to get a superposition state of some sort. So there are actually quite some cool experiments there that try to gauge whether we can build quantum systems that are big enough that the gravitational effects play a role on them, and while they are still in the quantum regime. And so that you could actually make a statement whether there is some quantum nature to the gravitational coupling or not. So this is all kind of stuff that's going on. And again here, I think new ideas would be desperately needed to expand the search. And with that, I basically end my talk. Thank you for listening.
You mentioned earlier that with a black hole, no light will come from a segment.
Yeah.
But according to Einstein, which has been proved multiple times, you have the gravitational lensing. So the light can come around. How do you account for that?
So this is essentially that here. What I have, let me show you. So, zip. So, okay, here. So the point is, light from here can reach us, yes. But we will see light that comes from here, we will see from that angle above here. So light that comes from behind the black hole, you will see above. The point is, this direction here will be dark no matter how much light is here.
Okay.
So,
I did
yeah.
appreciate that. Thank you. And a very quick one. What about the anti-Higgs?
Anti-Higgs, I'm not quite sure. Doesn't ring a bell, and I haven't looked into it.
I mean, it's theoretically possible.
I don't know. I have to pass on that.
Sorry.
Particle physics is the farthest away from what I've done so far. So,
Sorry.
anti-Higgs.
Yeah, anti-Higgs.
So there's the Higgs boson, and the question is whether there's an antiparticle. But I think it actually shouldn't be, because you have, I mean, you don't have an antiphoton, right? I mean, there just exist photons, and I think still different, still protons. So I think the Higgs particle goes into, so all the bosons I think are in this category, that they don't have antiparticles in that sense. But I'm not 100% sure. I bet there exist models that predict all sort of things, because there's like everything and the opposite that's been predicted. But so far what we have is the standard model. This is confirmed.
But the consequence of that, if it exists, it must create anti-mass. Higgs gives particles mass, so you have a negative mass.
This, right, yeah, I saw there were, I read recently some proposal of what would happen if particles with negative mass would exist. Answer to that, probably the best answer to that is general relativity doesn't allow it. So even if you look at an empty space-time that has just curvature in it, you can define asymptotically what the mass of the space-time is, and there exists a rigorous theoretical proof that if whatever is in the inside of your manifold follows Einstein's equations, then if you look at it, it's either the mass that you predict, that you see from the outside, is going to be positive. So what you ascribe to it as a mass will be positive no matter what. This is essentially, this is what general relativity tells you. So you, I mean, see, by the point where we're now, I think we have to be open to question almost every principle and everything, because so far nothing has really led to anything. But I think the positivity of mass, I'm not, it's one of the things that I'm less willing to give up. Let's put it that way. But fair, yeah. I mean, fair. People pursue the ideas. Let's see where it leads. I mean, there are some claims that if you plot, so there was this paper that if you take Newtonian gravity and you also plug in some negative mass, that you would get the same structure formation that we observe in the universe. So there are some of these claims out there. People are thinking about these. So far we haven't observed anything with negative mass here on Earth, so there would have to be somehow a mechanism that forbids negative mass things to interact with us other than through gravity, and Einstein's relativity doesn't really account for negative mass at all. So you'd have to somehow figure out why, if we look at everything around us, Einstein is correct, but you can on a global scale still get some effect that's close to negative mass, which I would say is a high bar, but sure, if people come up with consistent, yeah.
Thank you very much, but just out of interest, what's the speed, if there's anything that you're talking about, gravity waves in that sense?
What do you mean? What is their
What's
speed?
the speed of it?
So
Some people refer
is,
to it as like ripples on a pond. Well, what's the speed that it's travelling across the pond?
so that is actually one of the other results that I didn't mention about the multi-messenger astronomy, namely that it gives a very tight constraint on the speed difference between light and gravitational waves. Because basically you have, there is, I think the upper bound between that they could confirm from it was something like 2 seconds of difference. I think that is like, so there's a maximum of 2 seconds or so difference between when they saw, between the signal they see in the gravitational wave detector and the first light emission they get from that point. And since this is billions of light years away, this narrows down the speed difference to a couple, to quite a few digits behind close to zero. So roughly gravitational waves travel at the speed of light, I think. Plus, if you actually look at massive gravity, so there are proposals that that the gravitina, or that you have the messenger particle of gravity, if you believe in that, is massive. And I think there were all sorts of issues with that you get closed time-like curves, so you get time travel, more or less. But there, I'm not quite so sure. But just from this one observation, the mass, so basically, as a very first, to a very high degree, gravitational waves travel at the speed of light, period.
There's one other thing that I came across some time ago, or at least I think I came across it some time ago. I haven't been able to find it again since, and that is when you're looking at under the, where you get two protons that have been general relativity that are linked together but are separated.
You mean by quantum mechanics?
Yes.
Yeah. Yeah.
I saw a quote somewhere where it said that the speed of this interaction is not instantaneous, but it was 10 to the 17, I think it was, or about 17,000 times the speed of light, which is not instantaneous, but it's still bloody fast.
Well, I think what these experiments refer to is essentially you produce it's photons. So this is there's these experiments have been refined. There's a lot of them actually, but then to make it rigorous, that you have something that's kind of like instantaneous at a distance. So the technical term is that it's a non-causal interaction. So basically, just to prove that you have a pair of photons that's created as a pair. So they're created together. So, and the pair essentially has zero spin, but you don't know which one carries which. So now if you separate them, until you measure it, both of them have kind of a superposition of the spin, of spin up and spin down. When you measure this one here, and you find spin down, then that one here has to be spin up. And the point is, so you can So now the thing is, okay, you produce these two photons, you take them far enough apart, and now you make the measurement. And now to actually produce this to make this measurement in a way that you can truly say that no information from that measurement could travel over there is actually quite tricky. So this has been ongoing for quite some time. I think they have now more or less closed all the loopholes to really be able to say, okay, I observe here, I observe there. The superposition principle, so the breakdown of the superposition is observed, and so somehow, and then the claim is, yeah, well, okay, I observe here, this affects the state over there. Whether this is a legitimate interpretation or not, yeah, that's a good question. Whether it poses a problem, that's also a good question. I mean, certainly for Einstein's causality, so somehow the way we interpret it right now is that something that happens here affects something there quicker than light can travel. And that's essentially what's that spooky action at a distance, that the observation here gives us information about a point there which we cannot access by speed of light. Yeah, this is one of those experiments that one has to fit somehow account for. This is where the causality principle and general relativity, at least the most common, the Copenhagen interpretation of quantum mechanics and general relativity, are incompatible. But then again, Copenhagen is not the only approach to quantum mechanics. There are a whole host of different ones. I'm not quite sure what the ruling on causality violation is in different approaches to quantum mechanics. They all tell slightly different stories. But that is a whole different slew to go back to. But sure, yeah, these essentially superposition and observation. This the breakdown of the superposition under observation of a coupled pair of photons. This is one, or coupled pair of electrons. Any kind of two particle that you can separate, that you observe one and then you get information of the other, essentially boils down to something that we need to explain. Yeah. So that's out there.
Not trying to rain on anybody's parade, but it looks like we're getting to a case where the money involved in generating more and more information is we're getting diminishing returns. And when do we say, stop, that's enough, let's get off in a different direction, because who's going to pay for this?
That's a very good question. That's a very good question. That's why I have to say, I mean, this is, if you're keen at this kind of things, what I have lying at home, I've read good things about, it's Lost in Math by Hossenfellow, where she essentially discusses the problem what I kind of went on to in the end, where we're somewhat stuck, where, so spending 20 billion on an experiment on like, so with the Higgs one, it was essentially, okay, either we find it or our constant model, like if we don't find it, our current model breaks down. And however, now it's essentially, we're going on for an exploratory research. Whether 20 billion, I am not necessarily a fan of the Future Circular Collider. So the LISA proposal, sure enough, that will give us a lot of additional information where we know that it works. We know the sources of information is there. We can harvest it. It will give us new insight. We will learn a lot from LISA. This one, I think, is, I would not challenge. The Future Circular Collider, Yeah, 20 billion. I would not sign off, to be honest. I think we can get more with smaller experiments, tabletop, invest also in the model building again, go back to the drawing board and really think about. Well, I mean, as fundamental research is tax funded, right? I mean, yeah. No, so I mean, what you have to see with so these experiments as now, for example, in CERN, or I mean, one of the most interesting things that are developed are, for example, from the Event Horizon Telescope, the whole data analysis algorithm. It's also there, the signal to noise ratio is ridiculously small. So you have a lot of technologies, a lot of tools that are developed that I'm quite certain will have practical application. For LISA, it's actually all the laser technology that was developed. I'm quite sure this will have some sort of practical applications in communication technology and all sorts of things. Now, these side benefits are, of course, some of the considerations that come in when the foundational physics, basically it pushes boundaries. So you need to develop for the future circular collider, you would have to have magnets that give you 16 Tesla. They can also be used for MRIs. That gives you better resolution on MRIs. So you get a lot of kind of like spin-off research, but that by itself really doesn't necessarily justify building. Like, I think we can putting that money into fundamental research, sure. Spending it on one big circular collider, I think it's better to diversify. But that's my personal opinion. I'm probably not going to make some friends tonight if that video goes public. Okay, yeah.
Yes, could you, I got a little confused as to the degree to which we have established the superposition of electromagnetic radiation and gravitational radiation. The superposition, has it been established?
What do you mean by superposition?
In other words,
so I mean the neutron star observation.
Well, either the black hole, or
so the black hole only has a gravitational signal, but the neutron star collision, there we have a gravitational wave signal and electromagnetic signal that we can attribute to the same source.
And that's the one that has heavier metals than we...
Exactly.
Thank you very much.
Yeah. So that's basically what's come out of that. So that is, I think, truly in that sense, the first, or one of the first at least, events where the multi-messenger aspect really came to fruition. So this is, and I'm personal guess is that neutron star will at some point lead to another Nobel Prize probably, but it was quite funny. I mean, they observed it in summer 17, and they published the result only after the Nobel Prize for gravitational waves was announced. So I'm not quite sure whether that was political consideration to make sure that this result has not yet been covered. But these sort of things I think people do consider. So I wouldn't be surprised if the timing of the announcement would have some strategic considerations to it. But I wouldn't go as far as claiming that, to be clear. It's just it was an interesting sequence of events.
But could I clarify that there has only been one incident such as that?
I think there's one confirmed. I mean
One
now,
confirmed.
yeah. So one important thing we have now since beginning of April, there is the next upgrade from LIGO is online, and now it's spitting out black hole collisions by the week. So now we're really having weekly black hole gravitational wave signals that are incoming. Sometimes I think one they had twice a day. So we're now, so this next refinement upgrade put it really into the realm where, I mean, speaking of we get a statistic is probably still would be an exaggeration, but we are solid on the ground of this being a everyday thing. So nobody gets excited anymore about the black hole collision. I mean, so I think there was another one that was flagged as being maybe neutron star black hole, or being maybe something else than just ordinary black hole. But I don't think any of that has been confirmed. I mean, so now you get so yeah, there I'm not quite up to date, but I just saw some weeks ago that they now really have like events flowing out that's like, yeah, this is so gravitational wave certainly is one of the most exciting aspects of modern fundamental physics, I think.
Thank you very much.
Hi there. If I could go back, shot noise.
Yeah.
I'm a bit flaky on that, but it certainly came up in electronics, which I studied, and I think it's associated with amplifiers, quite often the active devices. I think fundamentally, and I'm looking up Wikipedia here, it comes due to the what do you call it? Particle type of nature of the flow of electrical current. In other words, the
I think here it is to the laser production.
Well,
or
I was going to say
or the
photon or electron.
Yeah. Flux.
The fact that it's quantized.
Yeah.
So I think that's
I think
quite often associated with active devices, and it certainly is used in the design of low noise amplifiers, and is modelled there.
I mean, there's one thing that I'm quite sure. So besides the whole noise device, this is this thing called quenched light. So they can somehow take the quantum uncertainty and put it into one side of the thing which they don't care about, and eliminate and boil and narrow down the uncertainty in the aspect of the laser output they care about. But my background on this stuff is not solid enough that I could give you any, but yeah, so if you're interested in that stuff, look up things, quenched lasers. This all relates, I think, to this shot noise issue and to reduce it. Yeah.
Well, you're talking a lot about money on experiments. What's your opinion of the billions so far spent on the James Webb Telescope? Is it is it justified? I mean, you can't stop it, but could it have been spent somewhere else?
So I mean, Hubble certainly has been, invaluable success, right? And I mean, Hubble is shutting down. This is matter of fact. So I think putting out a new telescope into space, there's there's probably another argument case to make here. There are increased problems actually with observations from Earth. Among others, I don't know if you guys heard of Elon Musk's new project, this star thing. This actually puts all radio astronomy on Earth onto a problem, because it creates an additional layer of noise that is directly, and that is everywhere. So now if you, at the moment you can go to Western Australia, you have a pretty radio quiet zone there. So that's why substantial are there, and like Atacama Desert. But Western Australia is actually pretty good for radio astronomy because there's nobody living there. There's no radio frequency noise, or very little. Now, if you put that in space and make a web around the planet, we basically get rid of radio quiet zones, which then forces telescopes into space. But yeah, so I mean, let's put it that way. The best argument for the James Webb Telescope probably lies here. Or for any telescope, in fact, the best hints we have at new physics comes from space at the moment. So, and there, of course, in all of our observations there, we have a problem, right, with the universe. We can't quite make experiments. There's one of it. And there's always, there's a lot of questioning, actually, that one has to be really careful when looking at the data that one gets, how much model assumptions have actually gone into the cleanup of the data, which is not always trivial. So when you look at when you're presented with the CMB data and they go like, okay, well, we have a model with only 6 parameters that match this observation perfectly. Then essentially what is not being told is that a lot of additional parameters went into the cleanup of the data. Of course, these additional parameters have additional constraints from other observations, but nevertheless, there's a lot more that goes into this final data than just that goes into the data set you actually match against the theory than just the 6 parameters. There's a lot of cleanup going on, and this is so yeah. I mean, there are people there has recently been I've seen there was an article by a philosopher of science questioning how solid cosmological studies really are, because how many priors and assumptions and bias actually goes into the interpretation of data. This is one thing. One has to look. There are efforts towards more model-independent studies of the observational data, which I think is very, very important. But so, I think this point here is really probably the best argument for more space, more universe cosmological observations, really, which includes the James Webb Telescope. Plus, of course, it just gives fucking amazing pictures. I mean, the best thing to convince a kid that physics and astronomy is cool. I mean, show them a picture of a galaxy. So like, that's out there. That's out there. When you look up in the night sky, that's what you can basically see. And that's super cool. Like all the pictures from Hubble. That does more to get people, and particularly kids, interested into science than any motivational whatever can do, right? It's like you fuel the curiosity by looking into space and by getting these amazing pictures out of space. So I think, yeah, I mean, okay, anyway, James Webb is on its way. Let's hope it will be as fruitless as the Hubble, and then we will have a lot, it will make us very happy, I think. So, yeah, but of course, these things, again, there, I mean, what is the value of it? These are things that one has to discuss, and as the experiments get more and more expensive, these are questions we have to face. And I think just saying it's worth it because it's fundamental physics, it's like, yeah, but to some extent, there's finite amount of money, and also, probably actually more important, there's finite amounts of brain power. Now the question is where as a research community, what problems do we want to focus our brain power on? I think that is an equally relevant question to ask, other than just the financial aspect. I think particularly, okay, I mean, you probably got it from that. I'm not a fan of string theory, and it has essentially absorbed an entire generation, particularly in the US, of theoretical physicists that is string theory and nothing else. When you look high energy physics in the US, it's either you do string theory or you don't you don't do it.
Any further I'm sorry, we're beginning to run out of time. Any other questions? No? One more, Gerard. Yep.
In your opinion, what do you think our chances are of continuing to be able to observe the universe to the degree that we need because of the pollution up there?
Well, I mean, this goes into a whole other issue of space pollution, right? I mean, this is actually there are studies whether how unstable the system up there actually is. So there are now so many debris particles. If basically, suppose if two satellites will crash into each other, two bigger ones, the cluster there is a non-zero chance that a bigger collision could actually trigger a chain reaction up in space, because every one of these collisions sets free a whole host of projectiles that will then trigger additional things. So I think this is actually before the observational become a problem. I think, well, okay, now Elon Musk stuff, there was actually quite some protests on Twitter when Elon Musk, when the first set was set up by astronomers particularly. There's quite an outcry going on that this is really a problem for them. So it depends certain frequencies. So but I think the space pollution by itself, not just on frequency, because so if you, I mean, this is also an operational thing. I mean, in principle, you can. I mean, these satellites are not necessarily indiscriminate, so you can make sure that certain areas are spared, which are. But essentially, you need like nature preservatories. You need radio quiet zone that are protected in pretty similar ways as anything else from pollution. It's a different sort of pollution. It just disables us. Well, I mean, it basically only disables astronomers, so it's not that fundamental. But still, it's just an issue one has to take into consideration. So if anything that you blast out might affect somebody. Yeah.
Okay, I think we'll have to call that a wrap. Thank you very much for that.